So we will talk about the cutting condition in turnings. So for the turning parameters, we have defined them last time in chapter 17. So we have the rotating velocity V. We have the feed F, which is defined as feet per revolution. And we have the depth of the cut. Now we will determine cutting conditions in turning. So the rotational speed in turning is related to the desired cutting speed at the surface of the cylindrical workpiece by the following equation. So we know that in this case we have rotation of the part, and then the frequency of rotation, the rotational speed can be expressed in number of revolution per minute. So in general, they can give us the number of revolution per minute, and we can deduce from it what will be the cutting speed, because you know that these two are related since n is proportional to the angular velocity omega. So if you know the number of revolution per minute, you can find the value of omega, which is the angular velocity. The angular velocity is in, let's say, in radiant per in radiant per second or radiant per minute. So let's say we are working in unit of minutes, then to obtain omega, it is equal to 2 pi times n, because when we multiply by 2 pi, then we will convert from revolution to radians. So we have here 2 pi radian over minute. So the unit will be radiant over minute. So we should multiply n by 2 pi. So when we do 2 pi times n, then the unit obtained will be radian per minute. Okay. Now we know that the velocity v is equal to omega times r. V is the linear velocity at the periphery. So to get v, we multiply the angular velocity by the radius, the corresponding radius of the work part. Okay. So let's say here we know the diameter. Then we can say that r is d0 over 2. So now, if you replace omega by its value, we replace omega by 2 pi n, then you will get that v is equal to 2 pi n times d over 2. So we will have simplification of 2. And then the velocity can be calculated as pi n d0. Therefore, we can find n function of v and d0 as n equal to v over pi d0. In this case, the unit of n will be in revolution per minute. The cutting, if you use for n the unit per minute, then you will have to, for the cutting speed, also to give it in meter per minute. And if you use n in revolution per second, then the cutting speed will be in meter per second. This is if you are working in SI units. If you are working in English units, then you can use for n, it's the same unit. Okay, it's revolution per minute. While for V, you can use then feet per minute, and then the diameter will be in feet. Okay, and in case you use SI, V will be in meter per minute, and then the D0 will be also in meter. So just you should pay attention for units here. And this is the relation between the rotational speed and the linear velocity and the diameter of the work part. Now, we know that during the turning operation, the diameter will be reduced. So we will go from an original diameter of D0 to a final diameter dF that is determined by the depth of the cut. So as you can see in the figure, the depth will cut from all sides. And here you have, if you look at the diameter variation, you should subtract 2 times the depth, because you have a cut here. And during the cutting operation, you will lose depth here and also at this level. So it's over the diameter, you will lose 2d. So the final diameter d will be d0 minus 2 times the depth. And sometimes concerning the feed in turning can be expressed in general in millimeter per revolution. So what we mean by this, so how much we are advancing, this is the feed. So how much we are advancing per revolution. So each revolution, I am able of removing a certain distance f. Okay, so now we can relate the feed to a linear travel time. What do we mean by this? So you have that in each revolution you are removing a certain length. So let's say you want to do the operation, the turning operation over a certain length L. Okay, you can convert. So if you want to know what is the advancing velocity of your tool, so how much I am moving my tool in millimeter per minute or millimeter per second, it depends. You can use whatever. So you can, if you know the value of f, if you know how I am advancing per revolution, and you know the frequency of rotation, fr, okay, the frequency of rotation can be related then to the feed, because the feed unit is a millimeter per revolution. Okay, and n, which is the rotational speed, is given in revolution per minute. So if you multiply n by f, then you will obtain how much I am advancing per unit time, because revolution will be simplified. Okay, so you have here revolution per minute. Revolution will be simplified, and then what you will get a certain velocity. The unit here of fr will be in millimeter per unit time. This means that what is the velocity of advancing of my tool during the operation, because you know that you will do a turn, and once it's done, your tool will go forward. Okay, if you want to know what is the velocity of motion of your tool in order to do the whole operation, so let's say you want to cover a distance L over your workpiece, then if you know the value of the advancing velocity in millimeter per minute, and you know the total length that you should go over, you can find what is the time required to perform this operation. Because if we assume v constant, let's say fr constant, you can write that L should be equal to fr times delta t of turning. Okay, so in this case, we say that we can express the linear travel rate of the cutting tool in millimeter per minute using the following form. Any question until here? Now, as we said, if you want to find the time to machine from one end of a cylindrical part to the other end, then we should apply the following relation, that the machining time required is the length over the feeding rate. Okay, and now if we replace in the expression of fr is determined function of the feed and the rotational speed. If I replace n by its expression, because we have already developed what is the equation of n, so if you replace n in your equation, then so first I put instead of fr n times f, and then I replace n by its corresponding value, which is we have developed previously, which is related to velocity pi and d0. It's v over pi d0. Okay, so we can just obtain the machining time function of the diameter, the initial diameter of the work part, its length, the feed, and the turning velocity. Okay, so it depends on the problem. What do you know? Sometimes if they gave you directly the feed rate and the length, so you directly apply this formula. In case they gave you other information, so it depends on your input. If you know the diameter, you know the turning velocity and the feed and the length, you can use this formula to determine the machining. And as always, pay attention for units. Be consistent in your units. So here, for example, if D is in meter and L is in meter, also F should be in meter and V in meter per second. Okay. So the overall unit for this term will be seconds. So the length unit should simplify, and we just should have at the end second or minute. It depends on the unit of V. If it's in a meter per minute, then all others should be in meters, D and L and F, and then the time will be in minutes. And if V is in meter per second and of course the other will be in meters, then tm is in seconds. Now, if you choose to work in inch, for example, in English units, then V will be in inch per second, let's say, or inch per minute, and all other dimensions, D, L, F, also should be in inch. Okay? Now, we have already developed in the previous chapter the expression of the volumetric rate of material removal. The volumetric rate of material removal is the velocity, the turning velocity times the feet times the depth, and its unit is millimeter cube or meter cube per unit time. So in general, we express it in millimeter cube per minute. It can be also converted to meter cube per second. Okay. Now we will see how to relate the removal rate to the other parameters. So sometimes, for example, let's say if you have the removal rate and you want to calculate the velocity, if they give you the removal rate, the feed, and the depth, you can conclude the velocity. So all these relations will, the use of relations will depend on your input. What do you know in the problem and what do you want to get? So instead of giving you the turning velocity, for example, they can give you the removal rate, and you will use it to find the velocity and then apply the velocity to use the other angles. Okay. Now we will move to cutting condition in drilling operation. So in drilling operation, the cutting speed is the surface speed of the outside diameter of the drill. It is specified in this way for convenience, even though nearly all the cutting is actually performed at lower speeds closer to the axis of rotation of the drill. To set the desired cutting speed in drilling, it is required to determine the rotational speed of the drill. So if we consider N as the rotational speed of the spindle of the drill in revolution per minute, also we can write its expression as developed previously. N is equal to the V is, as we said, it's the linear velocity at the outer periphery of the drill. D is the drill diameter. Okay, so we can then find the rotational speed of the drill. Now, also we can define feed in the drilling operation. So in the drilling operation, the distance that the drill will advance per revolution is given by millimeter per revolution in SI units and in inch per revolution in English units. It is recommended that we know that feeds are roughly proportional to the drill diameter, and higher feeds are used with larger diameter drills, since they are usually two cutting edge at the drill point. The uncut chip thickness taken by each cutting edge is half the feed. Okay. Now, the feed can be converted to feed rate as we did in the turning operation. So the equations are similar. We can get that the feed rate is equal to N times I. Now, in the drilling operation, we have several possibilities of making holes. Okay, so in general, we use drills to make holes. Now, sometimes we can do either through hole or blind holes, and we will see together what is the difference. In through holes, the drill will exit the opposite side of the work, so the hole will be over the whole thickness of the work part, while in blind holes it doesn't. So the machining time required will be different between the two, and we will learn how to determine it. Just let us see together the figure of the two operations. So you can see here we have these two types of operation. We have the first type is the through hole. When you do a through hole, then you will cut the whole part here. You will have hole from the upper to the lower part of your work thickness. And you will do the hole. The thickness of your holes will be equal to the work thickness. On the other hand, for blind hole, you will not go from one part to one end to the other. Your hole will stop in the material, okay, and it will be characterized by a certain depth, hole depth. Please here, we should pay attention here. The hole depth should be defined. يعني في غلط بالfigure here. The hole depth is defined just until here. We will see why. Okay, يعني D represents this distance. So because already D is counted from this position, from when the just the point of your drill is on the work part, as it will move, okay, this يعني نحن we count from the position where the point is in this position. يعني بنعتبر انه the drilling operation will really start بس يصير the full diameter of the drill is at the beginning of the work part. Okay, then from this position we should advance a certain distance d to make this whole thickness here. Okay, now let us develop the equations related to this operation. So in order to perform the drilling operations, we need to determine what is the machining time required to drill a through hole and what is the machining time required to do a blind hole. First, for the through hole, we have to account for two steps. As we said, first we should approach the work part. Okay, so we have a certain approach distance, which is the distance required to have the full diameter of the drill over the work part, and then we have the time needed to perform the operation. In order to determine the machining time, we should determine what is the total length that should be advanced by the drill point over the feed rate, okay? Because you know that the time is equal to a certain length, the total length that we should go over the velocity of advancing the tool, which is the feed rate F. So now let us see how to determine the two parts of the length. The two parts of the length which the drill will advance are the approach distance in order to just have the full diameter of the drill on the first level of the work part, and then T will be the thickness of the hole to perform. Okay, so Tm is the machining drilling time in minutes, T is the work thickness in millimeter or inch, Fr is the feed rate in millimeter per minute or inch per minute, and A, as we defined, is the approach allowance that accounts for the drill point angle, representing the distance the drill must feed into the work before reaching full diameter. So if we go back to the figure, this is A. This is the distance, the approach distance A. In order to have the drill in this position, where the full diameter will be at this level. Okay. In addition to A, after having performed the approach distance, we should move our drill through the. If in case we want to perform a through hole, we should move it further a distance equal to the thickness of the work. Then the total length here can be expressed as, in case of through hole, as the approaching distance plus T, okay, the thickness of the work. On the other hand, in this case, where we want to have a blind hole, first we should advance it a distance A. Once we have the advanced distance A, then this will be the position of our drill. The edge point will be like this, in this position. So now, in order to perform, to finalize the operation, then we should move this distance. Okay, distance D is from, if you want, the top to the full diameter of the hole. So this is the full diameter of the hole. This is D. So we should advance a distance A plus B. So just pay attention for this figure. D is until this level. Okay. Now we will have to determine what is the approach distance. The approach distance will be function of the geometry of the drill. Okay, so it will be function first of the diameter of the drill and the angle, the corresponding angle theta, because you have here, so you have a certain angle theta for your drill. Okay, the value of theta will affect the approaching distance. So the approaching distance in case of which is defined as the approach allowance that accounts for the drill point angle, representing the distance the drill must feed into the work before reaching full diameter, is given by 0.5d times tangent 90 minus theta over 2. Okay, where A is, as we said, the approach allowance. Theta is the drill point angle. So here we can define an angle theta. Okay, and you can easily theta, if you want, it is the whole angle, and theta over 2 will be this part. This is theta over 2. So if we look at the formula, it's very easy to develop. You have that this distance here, this is A. Okay, this is A. So if you look at this right triangle, you can write that tangent of this angle here, tangent of this angle is pi over 2. So this angle will be pi over 2 minus theta over 2. Okay. So tangent of this angle here will be equal to A, which is the approach distance, over the d over 2, which is the radius of your drill. From here, we developed the following relations, that A is equal to 0.5d, which is r. This distance here is r, times tangent of 90 minus theta over 2. Okay, so this will allow you function of the diameter and the drill point angle to determine what should be the allowance, approach allowance A. Okay. Now, once we have A, then we should move into the work thickness in order to produce a through hole. Okay, so this is the figure showing the details. You have, this is the point angle, as we said, and since we are considering A is this part, so we are interested in this angle here. This angle is theta over 2, because this is the axis of symmetry. It will divide the angle into two equal parts. And then this angle here will be 90 minus theta over 2. And we can just say that tangent of this angle is A over the radius, which is d over 2. Okay, so we got the expression of the allowance, and this will allow us to determine the machining time, because the machining time will be equal to the allowance plus, in case we have a through hole, as we said, we should add the thickness T over the feed rate, while in case we have a blind hole, which we should just add the depth, the whole depth. Yani we should have A plus the whole depth, which is determined from the bottom of the surface until the complete diameter of the hole. Okay, so here we will see the details of the equation. So as we said, in case of a blind hole, the depth is defined as the distance from the work surface to the depth of the full diameter. Okay, so please keep in mind to correct the figure. يعني هي مش to the point مش to the extremity of the drill, it's just to the depth of the full diameter. And in this case, the machining time will be equal to D plus A over FR. Okay, now for the removal rate, in case we want to find the removal rate expression, the removal rate in drilling can be determined as the product of the drill cross-sectional area and the feed rate. Why? Because you know that the removal rate unit is, it is in millimeter cube per unit time, second or minute. Okay, so if you want to compute what is the removal rate in drilling, you just have to account, when you consider the drill cross-sectional area, okay, then your drill will move with a certain velocity. So the removal rate will be equal to the cross-sectional area of your drill times the velocity, the feed rate velocity. Why? Because you have that, yani the linear velocity of motion, since the cross-sectional area will be in millimeters square. Okay, and the advancing velocity will be in millimeter per second. So if you multiply the cross-section of the drill by the advancing velocity, you will get, so you will get here a certain volume, and since it's per unit time, because the velocity is meter per second or millimeter per second, then you will obtain what is the volumetric rate يعني how much you are removing material per unit time. Okay, so this is why we can define simply the removal rate in drilling by the cross-sectional area of the drill times FR. Okay, the feeding rate, which is in the advancing velocity of the drill, which is a millimeter per second. And of course, this equation is valid only after the drill reaches the full diameter. So we should exclude the initial approach of the drill into the work, because already look, when you are just at this position, okay, the part that will be removed will be already accounted for after. لأنه once you reach the full diameter, you will start to remove the full part. يعني أول شيء أنتوا عم بتفوتوا شوي شوي you remove a small part لحد ما نوصل للcomplete diameter that will allow us now once we move حنرجع نشيل هول البارتس. يعني at the end when we find the total removed volume حيكون of it's a cylindrical shape. Okay, so in total we can assess it as pi d square over 4 times the feeding rate of the drill. Okay, so this is for the drilling operation. Now we still have the cutting conditions in milling. So milling will be the most complex one because we have several scenarios of milling. So first we will consider a slab or peripheral milling that will show how the cutting is performed. So depending on the type of milling, the position between the work part, okay, and the cutter position will be different. And if you have slab or peripheral milling, it's not like face milling. We will see what is the difference of relative position between the cutter and the work. So first, for case of peripheral milling, as its name indicates, we are removing material from a certain periphery of the work part. So here our purpose is to remove material from just one side. Okay. In order to perform the operation, the depth of the part to remove will impose what is the position of the cutter relative to the work part. So here, for example, if you want to remove D, then you should have the cutter position. If you want, we should lower it to a certain depth D. So this distance, so the cutter is at a lower level from the surface, equal in length to D. So this part should be equal to D. And then we will move the cutter over the work part in order to remove this material. Okay. Now, the parameters used in milling are the following. So first, to get the removal rate, for the removal rate, you have, so always, you can just derive the formulas when you understand what is removal rate. So as I am moving over this cross section. Okay. So as I move, I will have, in case, of course, if I consider that the length of my cutter will be larger than the length of my work part, in this way I can remove the complete width of the work part. Okay. So if in case if it's not, يعني مثلا if the length of the work part is larger than the width of the cutter, أكيد what will determine the length that will be removed هي الwidth of the cutter. Okay. يعني انتوا بدكم تشوفوا you should compare always the information that you have. يعني in case, for example, in case W of the cutter is smaller than the width of the work part حسميها WP. أكيد the part that will be removed هي الwidth تبعها حتكون W. Okay. Now, in case I have the opposite scenario, يعني in case the width of the cutter is larger than the length of the work part, فأكيد حيشيل بس على length of the work part. يعني imagine I have this إنه the width of the cutter أكبر من the width of the work part. يعني أكيد I will not multiply by the width of the cutting workpiece. I will just multiply by the width of the cutting إذا بدكم اللي هي in contact with the part. يعني إذا the part length هي L, so I should multiply by L. Okay. So here هون we consider in general إنه in a general formula إنه حنعتبر عادة بتكون إذا بدكم الcontact width يعني الcontact width between الcutter والwork part هي اللي that will be removed. So the removal rate then will be equal to W, which is the contact width between the work part and the cutter, times D, which is the depth of the cut, times the relative feet, okay, which is the relative velocity of approach between the work part and the cutter. ليش بنحكي ب relative؟ لأنه sometimes يعني مثلا أوقات في يكون الwork part fixed والcutter is moving، فيهم يكونوا بالعكس يعني فيها يكون الwork هي الموفينج والcutter بمطرحها. So what you will take into consideration here relative motion between them, or they can be اثنيناتهم they can be moving. So just you take the relative velocity, the difference between their velocity. Okay. يعني for example, let's say the cutter is moving at a velocity of 10 meters per second towards to the left, and the work is moving towards the right with a velocity of 5 meters per second. شو حتكون ال relative velocity؟ شو حيكون ال feed rate that I should take into account؟ How you calculate relative velocity؟ إذا هيدا ال velocity of the, let me check. Yes, exactly, Ghadi. It is 15. Okay, it will be 15 because you have V of the cutter and this is V of the work. So V relative will be equal to V of the cutter minus V of the work. Okay, and if we consider this is a positive direction, so it will be plus 10 minus minus 5. So it will be then 10 plus 5 equals to 15. Okay. So the relative velocity of motion will be 15 meters per second. So in general, the removal rate will be given by WD times FR. And as we said, this will neglect the initial entry of the cutter before full engagement. And this equation can be applied to all types of milling, end milling, side milling, face milling, and other milling operations, making the proper adjustment in the computation of cross-sectional area of the cut. So what will change from one milling operation to the other is the cross-sectional area of the cut. So we should see how to determine the depth depending on the type of milling operation. We will see the different milling approaches. So what will be the variation of D? What is the formula of D for the different cases? I will open a